The enigma of Pluto. Could a collision with Neptune reshape our solar system? In the vast expanse of our solar system, Pluto, a subtle and distant world, lingers on the fringes, captivating astronomers and the public alike. Once considered the ninth planet, this unassuming celestial body was reclassified as a dwarf planet in 2006, yet it continues to spark fascination and debate. Recent statements by prominent astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have thrust Pluto back into the spotlight, raising a provocative question. Could this far-flung dwarf planet be on a collision course with Neptune? If so, how could such a monumental event unfold, and what might be the consequences for our solar system, and even Earth? Is this a cosmic whim, a misunderstanding, or a genuine threat lurking in the depths of space? Join us as we explore the intricacies of Pluto's orbit, the gravitational dance of celestial bodies, and the potential outcomes of a Pluto-Neptune collision. Pluto, a dwarf planet with a storied past. Discovered in 1930 by Clyde Tombaugh, Pluto has long been a subject of intrigue. For decades, it held the status of the ninth planet in our solar system, a distant outpost orbiting the Sun at an average distance of 3.67 billion miles, 5.9 billion kilometers. However, in 2006, the International Astronomical Union, IU, redefined criteria for planethood, demoting Pluto to the status of a dwarf planet. This decision, championed by figures like Neil deGrasse Tyson, sparked controversy but highlighted the unique nature of this icy world. Pluto resides in the Kuiper Belt, a region beyond Neptune teeming with icy bodies and remnants from the solar system's formation. Unlike the 8 recognized planets, Pluto's characteristics, its small size, about 1,477 miles or 2,377 kilometers in diameter, icy composition and eccentric orbit set it apart. Yet, its reclassification has not diminished its allure. Astrophysicists continue to study Pluto, probing its mysteries and pondering its role in the cosmic tapestry. A troubling hypothesis. Collision with Neptune? Recent claims by astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited interest in Pluto, suggesting a startling possibility. A potential collision with Neptune, the 8th planet from the Sun Neptune, a gas giant with a diameter of about 30,760 miles, 49,528 kilometers, orbits at an average distance of 2.8 billion miles, 4.5 billion kilometers, from the Sun. At first glance, the idea of a collision between these two bodies seems improbable, even fantastical. After all, Pluto's orbit, while unusual, has persisted for billions of years without incident. So, how could such a catastrophic event occur, and why are experts raising the alarm? To understand this hypothesis, we must first examine Pluto's orbit, a path so distinct that it defies the norms of our solar system. Then, we'll explore the gravitational forces at play, the stabilizing mechanisms that have kept Pluto and Neptune apart, and the potential disruptions that could alter this delicate balance. Finally, we'll consider the implications of a collision and whether the scenario is a plausible threat or a speculative exercise in celestial mechanics. Pluto's peculiar orbit, a cosmic anomaly. Pluto's journey around the Sun is unlike that of any other planet. It takes a staggering 248 years to complete one orbit, a testament to its immense distance from the Sun. Since its discovery in 1930, Pluto has not even completed a single revolution, and it won't until 2178. This slow, leisurely pace is just one aspect of its uniqueness. Unlike the nearly circular orbits of the major planets, which lie close to the ecliptic plane, the flat plane in which most planets orbit the Sun, Pluto's orbit is highly elliptical and inclined. Its eccentricity, a measure of how elongated an orbit is, reaches 0.248, meaning it varies dramatically in distance from the Sun. At its closest point, perihelion, Pluto ventures as near as 2.76 billion miles, 4.44 billion kilometers, dipping inside Neptune's orbit. At its farthest, aphelion, it strays to 4.58 billion miles, 7.38 billion kilometers, far beyond the gas giant's path. This elliptical shape brings Pluto closer to the Sun than Neptune for approximately 20 years during each orbit, a phenomenon last observed from 1979 to 1999. Adding to the intrigue, Pluto's orbit is tilted at a 17-degree angle to the ecliptic plane, a significant deviation from the relatively flat orbits of other planets. This inclination, combined with its eccentricity, makes Pluto's path highly irregular, weaving a complex pattern through space. Such characteristics raise a natural question. If Pluto's orbit crosses Neptune's, why haven't they collided? The three-body problem and orbital stability. The stability of Pluto's orbit, despite its apparent chaos, is a marvel of celestial mechanics. To grasp this, we must delve into the three-body problem, a fundamental challenge in astrophysics. This problem involves predicting the motion of three celestial bodies, such as Pluto, Neptune, and the Sun, based on their gravitational interactions. Unlike the two-body problem, which has a straightforward solution for objects like the Earth and Sun, the three-body problem is notoriously complex, with no general analytical solution. The gravitational pulls of each body influence the others, creating a dynamic, ever-shifting dance. For Pluto, several key mechanisms ensure stability. 1. Asynchronous vibration. When Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune in its orbital cycle. This spatial separation prevents close encounters, reducing the risk of collision. The timing of their movements is not synchronized, a phenomenon sometimes called asynchronous vibration, though the term is more colloquial than technical. 2. Orbital precession. This refers to the gradual shift in the orientation of an orbit's closest and farthest points. For Pluto, precession means that when it approaches Neptune's orbit, it is often positioned far above or below the plane of Neptune's path, adding an extra layer of protection. This upward or downward shift minimizes the chance of a direct encounter. 3. VZK wobbling. Named after hypothetical scientists, likely conflation of researchers like Zeldovich, Kalipov, and others, with Michio Kaku's name possibly misattributed here. This concept describes a complex gravitational interplay among Pluto, Neptune, and the Sun. This wobbling reflects subtle perturbations in Pluto's orbit caused by the competing pulls of these bodies. Despite its irregular appearance, this wobbling contributes to long-term stability, keeping Pluto's path predictable over vast timescales. 4. Orbital resonance. A critical factor in Pluto's stability is its 3:2 resonance with Neptune. For every 3 orbits Neptune completes around the Sun, taking 165 years each, Pluto completes 2. This resonance locks their movements into a rhythmic pattern, ensuring that when Pluto crosses Neptune's orbit, the gas giant is consistently far away. This relationship, discovered through mathematical modeling, is a cornerstone of Pluto's orbital stability. The role of giant planets, Jupiter, Saturn, and Neptune. Pluto's orbit isn't stabilized by Neptune alone. The giant planets, Jupiter, Saturn, Uranus, and Neptune, play significant roles. Jupiter, the solar system's most massive planet, exerts a powerful gravitational influence, its pull helping to anchor Pluto's path. Neil deGrasse Tyson, a renowned astrophysicist and communicator, has long been associated with Pluto, notably for his role in advocating its reclassification as a dwarf planet. His work emphasizes the dynamic nature of the solar system, where orbits evolve and unexpected events can occur. Michio Kaku, a theoretical physicist, often explores speculative scenarios, blending rigorous science with imaginative possibilities. Together, their statements may reflect a thought experiment rather than a definitive prediction. In reality, the likelihood of a Pluto-Neptune collision is extraordinarily low. The 3:2 resonance, asynchronous positioning, orbital precession, and gravitational influences of the giant planets have kept these bodies apart for 4.5 billion years since the solar system's formation. However, let's entertain the hypothesis. What could disrupt this stability? 1. External perturbations. A massive object, such as a rogue star or large Kuiper belt object, passing through the solar system could alter Pluto's orbit. Such events are rare, occurring on scales of millions or billions of years, and no such threat is currently observed. 2. Chaotic dynamics. The concept of orbital chaos suggests that tiny changes in Pluto's speed or position could amplify over time, potentially shifting its orbit. Late 1980 simulations showed that while Pluto's path is sensitive to initial conditions, its long-term stability persists, making a collision unlikely within human timescales. 3. Unforeseen gravitational shifts. If the gravitational balance among the Sun, Neptune, and the giant planets were disrupted, perhaps by an undiscovered massive body in the outer solar system, Pluto's orbit could become unstable. However, no evidence supports this scenario. The consequences of a cosmic collision, if, against all odds, Pluto and Neptune would collide, the effects would be profound, though not necessarily catastrophic for Earth. Let's explore the potential outcomes. Impact dynamics. Pluto, with a mass of 1.31 times 10 to the power of 22 kilograms, is tiny compared to Neptune's 1.02 times 10 to the power of 26 kilograms, less than 0.013% of the gas giant's mass. A collision would likely see Pluto absorbed or shattered by Neptune, with minimal disruption to the larger planet's structure. Debris from Pluto, composed of ice and rock, could form a temporary ring around Neptune or scatter into the Kuiper Belt. Orbital ripples. The collision could perturb Neptune's orbit slightly, altering its gravitational influence on other bodies. This might affect the Kuiper Belt, sending comets or asteroids inward, though the chances of these reaching Earth are slim. Earth's fate. Earth, at 2.8 billion miles from Neptune, would be largely unaffected directly. No monstrous obligation to our planet, as speculated, is likely. However, long-term shift in the solar system's dynamics could subtly influence orbits over millions of years, a topic for further study. Scientific insight. Such an event, while dramatic, would offer a rare glimpse into celestial mechanics, allowing scientists to observe the aftermath and refine models of planetary interactions. The reality check, a cosmic whimsy, the stability of Pluto's orbit, reinforced by resonance, precession, and the gravitational choreography of the giant planets, makes a collision with Neptune highly improbable. Statements by Tyson and Kaku likely serve as a thought experiment, highlighting the dynamic and unpredictable nature of the universe. Neil deGrasse Tyson, known for making science accessible, may be drawing attention to the forgotten corners of our solar system, while Michio Kaku's speculative lens encourages us to consider what-if scenarios. Mathematical models and automated simulations, developed since the 1980s, confirm that Pluto's orbit, though chaotic in the short term, remains stable over billions of years. These tools, which tweak variables like position and velocity, show how delicate yet resilient the solar system is. The concept of orbital chaos, where small changes lead to vast differences, underscores the challenge of long-term predictions, yet no credible evidence suggests an imminent risk. Pluto's legacy, a window into the universe. Pluto, a dwarf planet on the edge of our solar system, remains a captivating enigma. Its eccentric, inclined orbit, stabilized by complex gravitational forces, exemplifies the intricate balance of celestial mechanics. The three-body problem, orbital resonance, and the influences of Jupiter, Saturn, and Neptune reveal a solar system in harmony, even amidst apparent chaos. The hypothetical Pluto-Neptune collision, while an intriguing idea, is not a pressing threat. Instead, it serves as a reminder of the universe's dynamic nature, where constant observation and analysis deepen our understanding. Pluto's journey, marked by irregularity yet enduring stability, highlights the limits of our predictive power and the wonders still to be explored. As we peer into the depths of space, Pluto challenges us to confront the peculiar properties of celestial bodies. Its orbit, a testament to the delicate interplay of forces, offers valuable insights into the solar system's broader dynamics. Whether through the lens of Neil deGrasse Tyson's public outreach or Michio Kaku's visionary speculation, Pluto continues to inspire, reminding us that even the most distant worlds hold secrets that shape our place in the cosmos. Embracing the cosmic dance. The notion of a Pluto-Neptune collision, while improbable, underscores the ever-changing nature of our universe. Pluto's orbit, a blend of chaos and order, reflects the complexity of celestial mechanics, where gravitational pulls, resonances, and wobbles maintain a delicate equilibrium. The contributions of astrophysicists like Tyson and Kaku fuel curiosity, encouraging us to question, explore, and marvel at the solar system's intricacies. As we continue to study Pluto, we gain not only a clearer picture of this distant dwarf planet, but also a deeper appreciation for the forces that govern our cosmic neighborhood. The universe, with its wild patterns and hidden rules, remains a frontier discovery, and Pluto, once a planet, now a dwarf planet, stands as a symbol of the mysteries that await.